Welcome back, ladies and gentlemen. In the previous lecture, we tried to figure out the answers to the question, why is spatial data so important, looking at business perspectives. In this lecture, we will discuss the answers to why spatial data is so important, looking from technical perspective. I will particularly focus on spatial data management and processing. The next slide will present the outline of the presentation. I will give you the answer from 4 different categories. Spatial data in database management system, which is about technical difficulties in storing spatial data in database management system. Topology of spatial data, which is about tight relationship among spatial objects, point, line, polygons. Spatial data indexing and related problems, and difficulties in applying multi-dimensional data indexing. Spatial Big Data Processing, thus problems and difficulties in applying data parallelism to spatial data. Spatial information is expressed in terms of point, line, polygon, or images. Point is a geometric element defined by a pair of x and y coordinates. Line is a shape defined by a connected series of unique xy coordinates pairs. A line may be straight or curved. Polygon is closed-shaped defined by a connected sequence of xy coordinates pairs. Where the first and last coordinates pair are the same, all other pairs are unique. Points, lines, and polygons datasets are not conventional data types such as numbers, date, and text string, which means that conventional relational data management systems cannot accommodate such datasets in the table. In fact, we can break down spatial data, in the case a polygon, and save it into tables as in conventional relational database management system, as shown in the figure. Topology deals with spatial properties that do not change under specific transformations. In geodatabases, the arrangement that constrains how point, line, and polygon features share geometry is called topology. For example, street centerlines and census blocks share geometry, and adjacent soil polygons share geometry. Topology defines and enforces data integrity rules. For example, there should be no gaps between polygons. It supports topological relationship queries and navigation. For example, navigating feature adjacency or connectivity, supports sophisticated editing tools, and allows feature construction from unstructured geometry. For example, constructing polygons from lines. Topological relationships are built from simple elements into more complex elements. Nodes define line segments. Line segments connect to define lines. Lines define polygons. A simple but naive representation of area features will be to list for each polygon the lines that describes its boundary. This is called a polygon by polygon representation. Each line in the list will be a sequence that starts with a node and ends with one. The reason why this is not a good representation is called data redundancy. This means that shared boundaries between polygons are stored double. Another disadvantage of such a polygon by polygon representation is that if we want to identify the polygons that border each other, this is difficult search analysis. When storing the second boundary, some line segments are duplicated. The boundary model or topological data model is an improved representation of polygon by polygon model. It stores parts of a polygon's boundary as separate line segments. Why is topology useful? Ensuring geometric correctness of data, detecting and correcting digitizing errors, carrying out some types of spatial analysis, selections, network analysis, find all light poles that are inside partial, find all the plots adjacent to a river, network analysis. Now let's take a look at issues of spatial data indexing. As B-tree is standard indexing method in conventional relational database management, R-tree, which is multi-dimensional extension of B-tree, considered as a de facto standard in spatial database management system. The figure contains quite a few spatial objects distributed in 2D space. The key idea of R-tree is to group nearby spatial objects and to represent them with minimum bounding rectangle, also known as MBR. In the next level of the tree, the figure illustrates how to group the given spatial object with MBR. The next figure illustrates the R-tree structure of the given spatial objects and MBRs. Leave nodes in the bottom store spatial objects. As with the other tree indexing, the searching algorithm is quite simple to check a search rectangle similar to B-tree. One major problem is that a very large overhead is required building R-tree. Can we apply R-tree to spatial big data? The answer is rather negative due to the high computation overhead. Now, let's extend our discussion to spatial big data computing based on understanding the nature of spatial data management. MapReduce has been the most popular programming framework for big data processing with a parallel and distributed algorithm on a cluster. Hadoop is still the most widely MapReduce framework using Hadoop distributed file system, also known as HDFS. Although Spark is gaining more and more popularity recently. The figure in the slide is a very simple conceptual diagram of Hadoop system for big data processing. As the name implies, MapReduce jobs are principally composed of two steps: the map step and the reduce step. The map step, which takes a set of data and converts it into another set of data, where individual elements are broken down into tuples of key and value pairs. The reduce step takes the output from map as input and combines those data tuples into smaller set of tuples. You can see a problem already. MapReduce uses only single key, which is one-dimensional, not two-dimensional key. Spatial relationship could hardly be considered and is not appropriate for spatial data processing. Overall, MapReduce is ideally suited for simple parallel computation on large size of data. But if computation that each node depends on data that resides on other nodes, the performance will be rapidly decreased. It is cut off for jobs such as web crawling, log analysis of typical big data processing, where dealing with velocity, volume, variety is more important than guaranteeing 100% data integrity and completeness. Now, my question is, how appropriate do you think is MapReduce? Maybe when dealing with spatial big data. In reality, a certain application of MapReduce to spatial big data problems came up with disastrous performance. Why? Because of the nature of spatial data. Strong spatial autocorrelation, interrelated topology, interdependency of spatial data components, which are hardly supported by conventional MapReduce framework. Then what will be alternative solutions? Well, alternative solutions are problem dependent. Sometimes even conventional Hadoop works beautifully for spatial big data problem which it deals with. For example, independent point events for noise removal, perhaps, and another value proposition of this course will be to make learners understand potential as well as the limitations of big data computing for spatial data. In this lecture, we have discussed the answer to the question, why is spatial data so important in terms of spatial data management and processing? All right, this is the end of the lecture. Hopefully you enjoy it. And if you've not subscribed to my channel, kindly subscribe, like, share to push me to go forward. And see you in the next lecture. Thank you.